Hello everyone. Um, Hi Karishma ma'am and Rishabh. Thanks for joining this session. So let's start the session by just formally introducing briefly. So as you already know, this is the weekly live session number 5 for the series for the course Affective Computing. And this course instructors are Professor Janendra Shukla from IIIT Delhi and Professor Abhinav Dhal from IIT Ropar and myself, Akanksha. I am a PMRF scholar at the Department of CSC and IIT Ropar. So today we will be discussing on a similar pattern as the previous sessions. So we'll be discussing different problems from previous year assignments from this week's content. Um, so let me start. This week is all about emotions in voice. It's like you have speech data. How can you use speech data? What are the features that can be used? Different data sets are also there. So yeah, these are the broadly the contents that have been discussed in the lectures. So let's start with the first question. And since Karishma ma'am is traveling, so if you're not able to answer, if you can type in chat and if that's okay, otherwise it's also fine. But I'll wait for a few seconds before explaining, just so get a chance to think about it. So let's start with question number one. Which of the following statements is true about fundamental frequency F naught? Fundamental frequency is also known as F naught. Option A, it is the frequency at which vocal cords vibrate in voiced sounds. It is the musical pitch of a note that is perceived as the lowest partial present. So A is correct, B is correct, both A and B or none of the above. I'll just wait for 10 seconds, 20 seconds. A. Only A. Okay. So let's see actually what fundamental frequency is. So what happens is in this image, you can see how we produce speech, how we produce our voice. So, uh, there is vocal fold vibration, airflow from lungs. So this is um, the signal. This is the signal that is produced by the vibration in the vocal cords. It has some frequency. It depends on person to person. Okay, this is called the F naught. Now what happens is that we produce a simple signal through when the vocal cords are like they are vibrating. So there is only simple signal, like as you can see, this is a simple wave, right? What happens is, how am I able to uh, pronounce different words or say uh, maybe sing or modulate the voice? It happens here. So we have our vocal tract. So here every human has different differently built vocal tract. Also, depending on the language and how we have been conditioned, so we kind of modulate that input, that basic simple signal, and then we can produce different sounds. So the speech signal that we can produce is that the source signal is transformed, and then we get the speech signal. Now this speech signal, it's not consisting of just a single frequency. It has multiple frequencies. It's a complex signal. this is a simple, you can say, simple signal, right? You perform some modulation here and then it converts to some complex signal. Now, since we have multiple frequencies, like if you want to break down uh, the different frequencies, so this signal might have this one high frequency. So suppose three frequencies are there, right? Um, what is the fundamental frequency here? Fundamental frequency is the lowest frequency. So in this case, this will be the lowest frequency at which a periodic waveform repeats itself, forming the basis of the pitch perception of a sound. Now, pitch and frequency are very confusing terms sometimes, but pitch is how we perceive that frequency, okay? Um, so this is the actual you can say frequency that consists of the major perception that we how we are hearing something, how something sounds to us. That depends on the a lot on the fundamental frequency, and rest the other frequencies are, maybe we can call them partials, or we can also call them some harmonics, and so there are so many like terminologies, different terminologies for that. But fundamental frequency is a very important feature that has been used by the researchers in the domain of speech processing, audio processing, because it is a indicator of overall how your you are kind of sounding to the other person, right? So, by definition, it is the lowest frequency at which a periodic waveform repeats itself, forming the basis of the pitch perception of a sound. Now, if we talk about the speech part, what happens is the fundamental frequency is closely associated with the vibration of the vocal folds or cords within the larynx. The voice box is there, and when a person speaks, air from the lungs passes through the larynx, causing the vocal cords to vibrate. There is a vibration, and this rate of vibration determines the fundamental frequency of the sound produced. Okay, this is in the case of speech. In music, also, fundamental frequency is relevant. It holds some meaning. So it corresponds to the perceived pitch of a musical note. If we talk about musical notes, there are C, C sharp, D, D sharp, E, F. So their musical notes are there, right? So every note, if you play, you will hear distinct sound, right? You will hear distinct sound. Now, what is that distinguishing factor? It is the fundamental frequency. Uh, it is what gives each musical note its distinct sounds and distinguishes one note from the another in terms of pitch. For example, there is a specific frequency, suppose 440 hertz. Since it is a frequency, like we measure it in hertz. Okay, it is measured in hertz. So, example is given like 440 hertz. It corresponds to the A4. Like if you know a little bit about the keyboard, you can imagine there is different octaves are there. So A1, A2, like that. So A4 is one note, and this particular frequency corresponds to this A4 note. So that is how we can kind of distinguish. For every note, there will be certain frequency associated with that. So it is fundamental because it determines the pitch of the sound, right? Pitch is the perceived frequency. For example, how sharp or how husky or different like characteristics, like how am I sounding? Usually, females have shriller voice, high pitch voice, and men have lower pitch voice. So, also, in addition to the fundamental frequency, complex sounds such as speech and musical tones, they also contain they also contain higher frequency components called the harmonics or the overtones, because as I already said, it's not a single signal, but it's a combination of signal, and there are multiple frequencies that are present in that signal. If you use Fourier transform, etc., to um, obtain different frequencies present in that signal, you may observe that there are peaks at certain frequency levels. And there's also some kind of pattern also, like harmonics is something, um, it is generally the some multiple of fundamental frequency. For example, if f naught is there, then one harmonic may be 2 into f naught, and then it may be 4 into f naught, so like that. Those frequencies are also usually present. So this is the overall concept of fundamental frequency. um, Example is also given, like it is measured in hertz. For example, fundamental frequency of 100 hertz means that a vocal cords are vibrating at the rate of 100 cycles per second. Okay. So moving back to the question, which of the following statement is true? Now, first is, it is the frequency at which the vocal cords vibrate in the voiced sound. That this is correct, right? This is true. And it is the musical pitch of a note which that is perceived as the lowest partial present. Partial means like if there is a complete signal, then we have some partial, you know, components of that. So this is the lowest partial. Uh, so yeah, this is also true. So both A and B are true actually. Okay. Now moving on to the next question. Which of the following are the examples of prosody features? Fundamental frequency, formant frequency, phoneme rate, all of the above. Fundamental. Okay. So let's discuss. Karishma ma'am is saying all of the above. So let's talk about what do you exactly mean by the prosody. So this term you must have seen in if you deal with speech analysis, music analysis, not music actually, or speech emotion or something. These applications. So prosody actually refers to the patterns of rhythm, intonation, stress, and timing in the speech. Um, there is a certain way of saying things. For example, I have some certain style of talking, right? And what I like to do, like I'm currently doing, is that I'm stressing on some particular words, right? This is what kind of a modulation of the words or the speech, right? So there is a pattern or there is a rhythm of the this speech. So it refers to the pattern of rhythm, intonation, stress, and timing in the speech. So it encompasses the melodic and rhythmic aspects of language that go beyond individual sounds and words. um, yeah, it's like overall how you kind of characterize person's speaking style, or like there is a pattern. So it plays a crucial role in conveying meaning, emotion, and emphasis in the spoken communication. When we talk to somebody, we're not just saying it in a plain manner, like, I will go to the park. No, there's some emotion, right? I will go to the park. So this is a modulation kind of rhythm is also there. There's a tone. Tone is also like you can consider like good tone. Sometimes we say the tone is very off, yeah, or they sound really rude, or that the tone was not what I it was not what I liked. So this is how we perceive the speech. So it includes, yeah, I've already discussed this speech variation and pauses, etc. So there are certain prosody features. Actually, all of them are prosody features. Firstly, we have already discussed about fundamental frequency. It is also a prosody features. It represents the lowest frequency of vibration. We've just uh, discussed that. It plays a crucial role in conveying intonation. And mind you that this fundamental frequency and all, we kind of change it like a high pitch and low pitch. It's not fixed for me. I can talk in high pitch as well. I can talk in low pitch as well. Depends on the situation, on the, for example, the emotion that I'm carrying. Uh, if I'm happy, then maybe I'll be shouting like crazy, and if I'm sad, maybe I will sound very, calm and relaxed or like slow. So it is a feature, okay. And then there comes the formant frequency. So it is the resonant frequency. One is fundamental, right? Then the other one is formants. Formants are, it is usually related to the thing that we have, the vocal tract, right? I told you, for example, there's an input straight signal, and then you kind of modulate it, and it converts it into some complex signal. For example, um, this is this is the input signal. This is very constant, right? And then vocal tract is there. It will kind of modulate depending on, this may be like that, something like that. So it can modulate it. um, it is the resonant frequency of the vocal tract that result from shaping of the vocal tract during speech production. It depends on how the vocal tract is shaped. uh, they have different frequencies like first and second formants. This is usually like, this is kind of a fact, that usually we use F1 and F2. They are have been proved, good for distinguishing different vowel sounds, and also considered as a prosodic feature. Now, phoneme rate is something that it refers to the frequency or the speed at which the phonemes is the smallest unit of sound that you can pronounce. Distinct speech sounds occur in the speech. It is also a prosody feature. It can indicate the rhythm and timing of the speech, okay, contributing to the overall prosodic pattern. So this is also prosodic feature. So the correct answer is D. Next question. If you attended the lectures, there was a data set discussed about for the speech data. So, what kind of data set is this IIT KGB Kharagpur SESC, this data set? There are different kinds of data set: natural data set, induced, simulated. If you attended the previous lectures, we also discussed these kind of data sets for the facial analysis and emotions, facial expression recognition actually. So there are data sets for that as well. There are similar terminologies here. So let's discuss. This is uh, the IIT Kharagpur simulated emotion speech corpus. Okay. This is designed for analyzing the emotions present in speech signals. It covers, okay, there are 10 professional artists. Now, if we talk about artists, it means they are professionally trained and they are kind of acting. For example, I hire people, I will tell them to say something in a sad tone. So, I went to the market. So they will mimic the sad emotion, and that is how you collect the sad data. Okay, they work on 8 different emotions using the neutral statements. They give the statements, and you have to say it in the different desired emotion. Okay, so it was recorded in Telugu language using the professional artist from AIR. So this is just the detail about the dataset. There are multiple datasets you can search on the web. So this is a simulated dataset. Yeah, Ravdis. So this is simulated because as it was mentioned that professional artists were there. So artists, they will enact different emotions, right? It's not natural. It's not natural, right? Induced, as the name suggests, mean that you show them something, some stimulus, and Based on that stimulus, they will respond in a certain way that you're kind of trying to induce. So this is not the case with this data set. So yeah, it is a simulated data set. Next question. Speech rate signifies loudness, pitch, voice quality, or velocity of the speech. D. Velocity. Okay. So let's discuss all of these features one by one. Okay. Um, First is loudness. It refers to the volume or the intensity of the speech, usually associated with the energy of this. Usually, like it's more related to the energy. Okay. Pitch is something that we already have discussed. It's the perceived. Perceived is the keyword. Okay. Perceived is the keyword. Perceived is something not objective. It is something very subjective. For some frequency might sound shrill to you, but not shrill to me. So this is a subjective perception. It determines how high or low it sounds. Okay. So we usually say high pitch or low pitch. One high pitch can be low pitch for me, may sound like that for me. But sometimes um, even a low pitch might be unbearable for me. I might feel that this is too high pitched for me. So it depends. Now, third is voice quality. It refers to the characteristics of the voice, like the texture of your voice, like if that makes sense. Um, coarse, how fine, how smooth or coarse your voice texture is. It's not really related to the speech rate, since the question asks about the speech rate. Now, velocity, of course, uh, it refers to the speech at a speed at which somebody speaks. I might speak slowly, and this is a slow speech. Also, I can talk very fast as well, like this is faster that I'm talking right now. So it is measured in terms of words per minute or syllables per minute. Okay. And it signifies how fast or slow somebody is speaking. So this is the velocity of the speech. Now, next question. Angry speech has a higher fundamental frequency, if not. Is it true or false? So basically, fundamental frequency can vary, as I mentioned briefly, that if you're feeling angry or if you're feeling happy, then your frequency can change, right? We don't talk on a same level all the time. We change, we tend to change our frequency. So, for this specific emotion, let's discuss anger and F naught. When we talk about the speech based affect analysis, uh, as I mentioned again, that there might be variations in fundamental frequency depending on the individual's physiological response and emotional state, how they're feeling right now. Now, some research studies they found that angry speech can sometimes be associated with higher fundamental frequency, especially in intense or aggressive expressions of anger. If you think about it, if you're angry and you like start shouting at people, right? So this shouting brings you, I mean, it kind of shifts the frequency to the higher spectrum. Your voice becomes more shrill, right? Um, it's not very calm. I hope I'm able to like make you understand that relaxed or something. When I say calm, it's more like this, like I'm talking right now. However, if I'm angry at some, I will shout like this. So my voice will become more shrill. So it will kind of shift the fundamental frequency on the upper zone. So this may be attributed to the physiological changes as increased muscle tension. There might be reasons for that in the vocal cords. So this might result in a higher pitch. Uh, of course, it's not something universally true. You can't say it will happen to everybody, but in general, most of the cases it happens. Okay. Emotions in general are very you can't generalize, so it's very subjective overall. However, there is some certain up to some certain level we can generalize things. There is a specific pattern, like if you sound happy, you can sense that people are happy, right? Maybe it's not exactly the same for everybody. So there these differences will always be there, but um, in general what happens is that anger and f naught, it leads to a higher fundamental frequency. Okay. Now, in iterative feature normalization, observations that are labeled as neutral are used to re-estimate and normalization, re-estimate the normalization parameters. Is it true or false? So let's jump to this iterative feature normalization. What happens is that, in general, what do you mean by feature normalization? Suppose you have a data set where we have speech data, emotional speech is also there, and some audios may be happy, some may be sad, some may be angry, some may be neutral, right? And you want to normalize the features. Suppose anything is there, for example, you've extracted mfcc or um, any feature for that matter. Okay, now you want to normalization in general. What it does is that it makes our life much easier because we can eliminate the unnecessary um, factors of variation which can impact adversely on our model's performance. If we manage to make the data in uh, for example similar range overall. For example, we most of the time we do in like between 0 to 1, we convert the values to 0 to 1 so that to obtain a standardized or more normalized um, representation. For this, there are actually two strategies in case of speech, major strategies, I would say. First is iterative, and the second one we will discuss in a while. Now, iterative, as the name suggests, we do it iteratively, means in a loop or multiple times, I should say. So, how it happens is that initially, what we do is initially we extract the feature, right? Acoustic features are extracted from the speech signal without any normalization. Now, emotion detection is applied. We can detect segments labeled as neutral and emotional. So, what we can do is separate the neutral and any emotional data, right? This can be done using emotion recognition models that have been already pre-trained, I mean, in for that particular uh, goal. So, yeah, we can classify into emotional states. Now, the best way is that we take only the neutral samples as baseline. Okay, why are we not considering the emotional state? Because as we discussed that it is also possible that one speaker, their frequency or their features will be different. They will talk differently if they are experiencing some kind of extreme emotion, right? But in normal conversations, what happens is we are more, it's more kind of natural, right? It's more true to them. So we can obtain more true to true to that speaker. We can obtain that feature from the neutral speech. So we generally prefer to use only the neutral samples as a baseline. They are considered as baseline on the reference point for the normalization. Now they represent instances where the emotional content is minimal or neutral. Now, the normalization parameters, we calculate like mean. Okay, we have all the neutral audios. Now we can calculate, okay, what is the mean value for the fundamental frequency, suppose, right? I get some F value. Now, I can use that and the standard deviation, etc., to normalize. Like I can subtract from the mean and then obtain a value which is lying between a certain range. So this is how we can uh, this is one method is z-score normalization, and there can be multiple strategies. So by focusing on these neutral samples, the normalization aims to capture the typical characteristics of speaker voice when expressing minimal emotion. As I already mentioned, that it's more true to them. It's normal, like I'm talking right now. This is my normal voice, actual voice. Um, Now, this is an iterative process. This is repeated iteratively, and with the updated normalization parameters, we want to renormalize the entire data set. This is what happens. Now, the goal is that we try to improve this normalization because there are a lot of variations in the speech data. So somehow we want to do it in iterations. Now, when do we stop? We stop when certain percentage of files in the emotional database having their labels changed from one iteration to the next. This ensures that the normalization the process stabilizes and achieves a consistent representation of speech features across different speakers. Actually, we will discuss about this thing in detail in a upcoming question. So I think you will be able to understand more. So this is the overall idea of the this iterative feature normalization. This is we calculate the features. Normalization is that we use an automatic emotion speech detection, which can give us the emotional speech and the neutral. So now we are using both, and we say, okay, have the labels changed? Like whatever we are doing the downstream task, do we are we getting good results? If not, then uh, uh, then we can, I mean, stop. If yes, then we can estimate the parameters for normalization, and again the cycle continues. This is slightly confusing, but I hope it will be clear in the next questions. So this is actually true that iterative normalization, they are labeled as neutral, that are labeled as neutral are used to re-estimate the normalization parameters. This is true. Okay. Next question is, identical feature normalization can adversely affect the emotion discrimination of the feature. Now, this is the second strategy that I was talking about. This is identical feature normalization. What it does is It's a method to normalize features across different samples or instances within a dataset. As the name suggests, we apply similar kind of normalization to all of the um, samples or instances. Okay, normalize feature across different samples or instances. And the normalization parameters are computed based on the entire data set rather than specific subsets, because in the iterative one we had a neutral and emotional subsets, right? And we only use the neutral one. But here we apply on the overall data set. So how does it work? We extract the acoustic features, then the normalization parameter computation, it's like min max, or you just calculate the deviation, mean, these things. So this step aims to capture the overall distribution and variability of the features across all the samples. Now we want to normalize. We have the mean value, we have standard deviation, so we can use that mean value to compute in a certain range. Like I mentioned, we can subtract the values from the mean value and then uh, use that new value as a the normalized feature, to be precise. So they are standardized and they're scaled consistently across all the samples. Now we have the normalized data. We can use it for any other application. New data we can use. So parameters are computed and applied to the data set. Then same parameters can be used to normalize feature values from new or unseen data. This ensures consistency because you are considering the whole data set. Of course, it will be more consistent. So this is more of a global approach, global normalization schemes. It treats all the samples equally and it does not differentiate between subsets or segments. While this is a very simple approach, just do it for every sample, it may not capture the specific variations or characteristics present in different subsets of the data, such as differences between neutral and emotional speech segments, because it might remove important variations in features that are crucial for distinguishing between different emotional states. Because since we are you know we have emotional data, we have happy data, we have neutral data. Now happy will have certain kind of distribution, right? And those characteristics will be the representative of that happy class. There might be some features for that. However, if we are like considering the overall normalization, we are kind of ignoring the fact that they might have some important information related to the emotional aspect as well, and we are ignoring that, and we are just overall considering the overall mean value. So I will take the help of an example. For example, there's a neutral audios, and this is suppose happy audios. So for example, the mean value of certain feature is 10 here. However, the mean value is, if we talk about individual classes, subsegments, this is suppose 5. But now the overall will be 7.5. Now we have kind of increased the value uh, for the neutral class and decreased for the happy class, right? So this will lose the information about the individual characteristics of the two classes. So this is the disadvantage of this identical feature normalization. Although this is very easy to implement as compared to the iterative one. So read out the question again. Identical can adversely affect the emotion discrimination of the feature. This is true. Next question. Which of the following are true? Positive voices are generally loud with considerable variability in loudness, have high and variable pitch, and are high in the first two formant frequencies. Variations in pitch show differences between high arousal emotions and low arousal emotions when compared with neutral vocalizations. So, what do you think? Which statements are true? Both. Okay. So if we talk about the positive voices, what happens is that there are certain characteristics we can imagine also, we can relate also. Usually when you're happy, you're shouting. Okay, this is again not for every person out there, but most of the cases, right? Overall perception. So often we talk loudly, right? Louder, indicating higher energy. We are more excited, so we can talk loudly. Uh, we are feeling happy, so expressing it with higher energy in the speech signal. Now, there is a variability in loudness, considerable variability, because suppose you are sad, so you will slightly talk like this. Um, Positive voices typically exhibit the following characteristics. This sounded more like a constant, uh, you know, loudness, or there is no, I shouldn't say no variability, but very less, right? This is very bland. However, if I'm talking like I'm very happy right now, so I will modulate my voice a lot more than what I was doing when I was sad, right? So there is a considerable variability in the loudness of positive voices. We It reflects the dynamic nature of the emotional expression. We are more expressive, right? Then there comes pitch. Positive voices, we are more happy. We can shout also sometimes. We are very excited. So it tends to have a higher and more variable pitch. There are fluctuations in the fundamental frequency of the voice, right? And for the formant frequencies also, it also represents the resonant frequency. They contribute to the okay, we know that. They are also high. Okay, they're also high. And if we talk about the excitement or the arousal part, high arousal emotions, they are usually more pronounced variations. As we talked about, even if you're angry, which is a negative emotion, and if you are surprised, for example, these two are high arousal emotions, right? How high arousal emotions like joy, they are more pronounced variations. We just realize that I will make more modulation in my voice, right? And it results in wider range of pitch frequencies compared to neutral vocalizations. And on the other hand, low arousal emotions like tenderness, they may exhibit smaller variations in pitch and more subdued and stable vocal expression, right? This is intuitive enough, right? So, yeah, both A and B are true. Let's read them once again. Positive voices are generally loud with considerable variability, true, right? In loudness, have high and variable pitch, yes, and high in the first two formant. This is also true. Variations show differences between high arousal emotion and low arousal when compared to neutral vocalizations. Yes, we can compare them with the neutral state and we can observe the differences. So, yes. To account for variations brought on by the speaker's vocal qualities, speaker normalization is applied. This is true or false? Okay, so let's talk about speaker normalization. Um, why do we need normalization? Let's discuss it again. Speaker normalization is applied to account for variations brought on by the speaker's vocal qualities. This normalization technique, we want to mitigate the differences in speech features caused by individual differences in vocal characteristics and speaking style. What happens is that if you collect data from a set of 10 people, every person will have different voice, right? Different pitch. But then how do you generalize something to a certain level, of course? How do you do that? Because they are already very different from one another, right? So that is when we kind of consider normalization, because we want to mitigate the impact of um, all other factors. For example, okay, we will see an example in a while. So let's read this first. Normalization, the features across different speakers and the influence of individual vocal qualities on the analysis should be minimized, allowing for more accurate and consistent results in tasks such as emotion recognition or speech processing. So your happy might sound different than my happy, right? So we want to consider only those factors which represent happy and which are not representing the speaker differences, if you're getting me. um Example. Okay. Okay. So yeah, as I mentioned, like me, you, and me, Karishma ma'am, and Rishabh, we all will have um, different frequencies, different speaker characteristics, right? Because we have different voices. However, there will be some kind of pattern. For if we are talking about the same emotion, happy emotion, sad emotion, so we just want to focus on that relevant information which represents or which is relevant to the emotional part, because my task is to detect the like emotion recognition is my task, right? I don't want it to be specific for certain speaker. It should be generalizable. So how do I generalize the concept of different speakers but retain the valuable information which can tell apart different emotions? That is when we need normalization. We want to reduce the impact. So for example, your um, certain features will lie in a different range, and mine will lie in a different range, and ma'am's will also lie in a different range. So we can do is we can normalize our three features and then use that for the emotional recognition part. So that is how it will be more efficient. Okay, so this is true. So next question is, women's voice have a lower fundamental frequency than men's voice. True. Are you sure, Rishabh? Lower, lower fundamental frequency. Usually, yeah, it is false, because usually women have more shrill voice, high pitched voice, and men usually like they tend to have, yeah, they tend to have low pitch voice. So lower fundamental frequency for the men's voice, and high fundamental frequency usually for women's voice. Okay. So, just to read this out again, women tend to have higher fundamental frequencies or pitch in their voices compared to men. This means that the vocal cords of women vibrators are at a higher rate of men, resulting in higher pitched voice. So, this is the typical range observed for men and women. So, you can see almost double, right? Yeah, so this is also a nice discriminating factor, because we can use this aspect in different speech analysis and different tasks as well. So yeah, this is one this can be used as a feature as well. Okay, so this is false. So, what is the primary motivation for pursuing voice as a primary modality in affective computing? Okay, this is so. First is facial expressions are unreliable. Voice analysis can provide value information for about emotions even without observing facial expressions or gestures. Voice analysis is less intrusive than facial expression analysis. Voice analysis is more accurate than other modalities. B. Okay. So, yeah, yes, your answer is correct. Let's go through the points one by one. Why do we need voice as one of the primary modalities? Okay, because we last week we discussed in facial expression recognition, right? We need cameras. We need to capture the facial, information. But there are some challenges associated with the facial expression recognition system because one is um, FERs, FER challenges. One of the biggest challenges, like if obstacle is there in front, your face is hidden. You can't, like, there is a physical object present. Okay, you can't, capture the face. So how will you actually know how the person is, like, you can't capture the expressions, of course there's no point. You can't tell how the person is feeling just by looking at their face because you're not actually looking at the face, right? This is this is one major problem. Are facial expressions unreliable? No, they are not unreliable. We can use voice analysis in addition to FER also. So it's not exactly an alternative. It's not an alternative, but you can use both modalities as well, right? Or you can use the single modality when the other modality is not present. Like I already mentioned, suppose you are capturing, you're recording this session and somehow um, maybe okay, you're talking to your friend over a video call. Now there is some issue with the quality of network is not there, and the video gets disturbed, but you can't look at their face. However, you can listen to their voice and you can sense that, oh, you seem a bit low, what happened. Similarly, we can use it for the this affective computing as well. Like we can use the characteristics of the voice. Like we have so many emotion recognition models already working. Also, you can design your own model for this purpose for specific applications as well. So we don't need to observe the facial expression or gestures, right? Without observing, this is less intrusive than facial expressions. Okay, this is true, right? Voice analysis is less intrusive. No, it's not less intrusive. Both are equally non intrusive, right? You're capturing the facial expressions, you're not being intrusive. Intrusive in the sense you're not putting some sensor on your body, right? It's just capturing through a camera, it's not intrusive. Also, for the voice, also, you're not using something to, you're using a microphone, right? You're using a microphone. to capture you, maybe a mobile phone recorder. So non-intrusive, no, this is false. Okay, and voice analysis is more accurate, no, it's not like that. You can't say anything more accurate or less accurate, right? So yeah, B is the right option. Next question. Which scenario illustrates the use of affective computing in indexing videos? First is analyzing facial expressions of actors in movies, identifying keywords in movie scripts, searching for videos based on emotional content such as happy events, creating subtitles in different languages. Rishabh says C. Karishma ma'am C. Okay. Okay. So if you talk about video streaming platforms, such as Netflix, Prime, Amazon Prime. So you, if you use them, you might have noticed that somehow they have a category based on the emotion as well. Like, are you feeling happy or something like? There is a possibility that you might find that. I'm not sure which platform was that, but yeah, if you like happy or sad or whatever the emotion you're feeling, you there was categorization based on this emotional aspect also, right? So how do we do that? We can use affective computing for that, because we can analyze the videos, right? We can analyze the videos, get the overall emotional content. For example, how can you do it? Like, if we just talk about very rough overview of how are we going to do it, very very basic. Just split the videos into multiple chunks, okay, smaller chunks, process each chunk separately. um, you can kind of use any model to analyze that. Okay, this is happy, sad, happy, happy. Then you can for example, there are 100 chunks, you can take the majority of that, like overall emotion you can use by voting or final decision fusion, whatever you want to. So this is just an example how you can obtain the overall emotional message, or that intent that the video is carrying or the movie is carrying, right? So you can browse, you can categorize your content based on the emotional component present in that particular content. Yes, exactly, exactly, exactly. Even song like, so how are you? I was actually talking about Spotify. I confused it with Netflix. But yes, you're absolutely right. Spotify does that. How are you feeling? And then you can like, okay, use that particular playlist. It will enhance your mood or like that. So yeah, so let's read this out. Searching for videos based on emotional content, it involves effective computing techniques to analyze the emotional expressions, tones, or other cues within videos to categorize them based on emotion they convey. Mostly, what happens is for videos, we generally use both audio modality and the image or the video like modality, because uh, obtain we can obtain an overall emotional overview, right? How that excuse me, how that what I mean, what emotion is being portrayed in that movie. So you can uh, check the audio signal as well as the images, facial expressions, and then fuse the decision. For example, a video indexing can analyze the audio visual content to detect emotional cues such as happiness, sadness, excitement, or fear. For example, a comedy movie, the non-verbal cues may be laughter or uh, chuckles. So these kind of non-verbal cues can also be there. You can analyze that as well. You can count. okay, how many times did this crying or sad music is being played. So music analysis can also be there, right? So multiple methods can be deployed. um, Users might be able to enter keywords like happy, exciting, or uplifting. I'm feeling very low today, so I want to listen to uplifting music. So this, like Spotify has an uh, workout or like uplifting music also, so that they will boost your mood accordingly, right? They evoke the positive emotions. So yeah, this is uh, are you able to listen to me right now? I just got a message. Maybe then there is some issue with my network. Okay, okay, cool, cool. So yeah, so what happens is that if we are able to categorize them based on the emotions they convey, we make it easier for the users to discover the content which, like, I am feeling low, so I want to watch a motivational movie, so I can kind of connect more with that. So yeah, so this is about the indexing. Okay, so uh, analyzing facial expressions of actors in movies. Okay, identifying keywords in movie scripts, that can be done, that can be used actually. Searching for videos based on emotional content, yeah, this is, see, actually it describes the in the best manner. Other first two options are like they can aid you to design the system, but they're not exactly how indexing. You will describe indexing, right? And creating subtitles, no, this is not correct. Okay, how is effective computing utilized in automatic translation systems? By translating between languages, by ignoring emotional nuances, by analyzing the emotional and behavioral aspects of communication to enhance translation accuracy, by focusing on linguistic patterns to ensure accurate translation, all of the above. Okay, B. Yes, this is correct. So we can, one thing is just the translation, but if we are able to capture the emotion, uh, you know, that one person is conveying through the speech, and then we can also pass it after the translation as well. So the message will be conveyed in as it is, that with the same intent as the speaker intended to. So that is one plus point, and it will enhance the overall experience of the ATS, automatic translation systems, right? So we not only we analyze the linguistic content, but we also the emotional and behavioral cues present in the communication, right? So we can use, for example, language one to language two, Hindi and English, suppose, and there's a translator, and somebody is saying something in English. So different languages can have different contexts, different interpretations for the same things, right? But we need to get that right. Um, we what we need to understand is that the intent behind the what the speaker was saying, and we if we understand if we understand the emotional nuances of the text, these translation systems can, they provide more accurate and contextually appropriate. This is actually the most important thing here, contextually appropriate translations, because again same intent is being delivered, right? And we can capture the full meaning and intent behind the communication, more effective translation outcomes, resulting in more effective translation outcomes. Um, so this enhances the overall experience, right? By translating between, okay, by analyzing the emotional and behavioral aspects of communication. By translating, ignoring is no, because this is going to, I mean, not a good experience. And by focusing on linguistic patterns, this is necessary actually, but not sufficient, right? We need to include emotional understanding as well. And how affective computing can help, right? Okay, what are the three major factors identified by Borden and others as challenges in understanding emotion through voice? Is a speaker's accent, pitch, volume, speaker's age, gender, and cultural background, the content of the speech, paralinguistic information and the speaker's attributes, speaker's emotional state, tone, and body language. C. Rishabh says C. Okay. So there are certain challenges in understanding emotions through speech. Um, this Borden and colleagues, they identified three major factors that can cause challenges in understanding emotions through voice. The first is the content of the speech, what is being said, right? Second is the paralinguistic. Paralinguistic means other than the semantic information, like other than the what things are being said, right? The, other than the linguistic component, paralinguistic, which means the intonation, prosody, okay, and the speaker's attributes, the context, their background, their gender, their age. A lot of things affect that constitute the context. They also have, uh, I mean, there is a challenge to understand that as well, because one thing said in one environment may mean completely different than the other, uh, than the same thing um, said in a different environment, because at one in one environment it might be sarcastic, but in one environment it can actually be the, I mean, exactly the same meaning as it has been said. So this is very crucial to include all these, to just take care of all these factors. We will look uh, into more into this using an example. Okay, for example, what is being said, what is said. Suppose I am feeling happy today. This is very straightforward, right? Very straightforward. I am feeling happy. Happy itself, it's describing the person is happy. It is very straightforward, conveying a positive emotion. However, if the speaker pronounces the words with a flat tone or a monotone voice, it may be difficult for a listener to, or an effective computing system to detect the underlying emotion. If I say, I am feeling happy today, this sounds more like a neutral state, not a happy one. So, but we often, the intent is happy, right? I mean, I did not use that prosody, but there's a mismatch, you can say. So, in order to understand that mismatch, we need to consider what is being said. Is it happy? So, yeah. Now, how is it said? There are two scenarios when a person responds to a question like, yes, I agree. In the first scenario, the person says it with enthusiasm and a confident tone, like, oh, yes, I agree. Okay. And indicating agreement and positivity, right? In the second scenario, there is more hesitant or subdued manner, like the person is underconfident and suggesting uncertainty or lack of like conviction. Okay, same words are being used, but the emotional tone, that is, it's different. It's different. Um, yes, I agree. Maybe this might sound different than what I previously said, right? So there's another challenge. And third is who says it. Um, Depends on the context. Okay, suppose there are two individuals, different ages, one teenager and one elderly. Both say, "I'm not feeling any pain." The emotional context conveyed by each speaker may vary based on their age and life experiences. The teenager statement we can interpret as casual or less serious, right? But the elderly person's statement might carry more weight, possibly like they are indicating the resilience in the face of pain. Like they can mean in a different way, the depth can be different. So these factors are also there. So mainly three factors were there. So if we go back to the question, so yeah, C is the right answer. Accent, pitch, and volume, no, it's not the given by the Borden and others. Speakers' age, gender, and cultural background. This is one thing, right? But this they don't consider the content, etc. Paralinguistic. So this is the correct answer. Which of the following best describes the challenge of how it is said in understanding emotion through voice? Analyzing the speaker's accent and pronunciation, understanding the speaker's tone and manner of speech, recognizing the linguistic origin of the words spoken, identifying speaker's age and gender based on voice characteristics. What do you think? B. Hmm. Correct. Correct. So, yeah, challenge of how it is said. It we need to consider the paralinguistic aspects of speech, such as tone, intonation, rhythm, and other vocal cues that convey emotional information, right? This includes factors like speakers, pitch variation, tempo, volume, emphasis. Like this is all under the umbrella of prosody, right? And overall manner of speech. These aspects play a crucial role in expressing emotions through voice and are essential for accurately interpreting the emotional content of speech, right? We have already discussed about this. So B is the correct answer. Okay. Which category of voice based data involves inducing emotions in participants through stimuli such as videos and then capturing their speech responses? B. Simulated. Okay. Okay. Karishma ma'am is saying D. Rishabh is saying B. So let's see. We have different types of speech data, right? First is natural data, naturally occurring speech data, where the emotions are expressed without any external influence or stimuli. Um, Suppose we are talking over phone, I'm calling you, and we're talking, having normal conversation, and then the call recordings are considered as speech data. because I was not expect, like, it's not something I know, okay, this is for a data set. No, this was our natural conversation, so I will be more expressive in the most natural form, right? Like interviews or public speeches where individuals express their emotions spontaneously. It's not planned or simulated. Now, second is simulated data. It involves generating artificial speech data that mimics real life scenarios or situations. So the term text to speech is very, like, is a buzzword right now, and now we have such good quality text to speech systems that we can produce such realistic voice that you can't be able to distinguish. Okay, so this is one, for example, if you want to expand your data set, and you don't have Hindi data set, now it's very difficult to record people, hire people and get Hindi or like that. So you have a model trained already for text to speech in Hindi, suppose. Now you can type anything in Hindi and it will say it out loud. It will convert it into speech. You can add this to the data set. So that is how you can produce as many audios as you want with good accurate, I mean, with good quality data, because TTS, they have, progressed a lot. So you can use synthetic voice and generate speech with emotional characteristics also. Nowadays, TTS systems are emotion enabled as well. Like you can say, okay, this text in happy tone, so it will convert into happy emotional speech. And scripted is predefined scripts and all to elicit specific emotions. Um, Actually, the last one is the most relevant for this question, because elicited emotion data, it involves specific emotions through controlled stimulus such as videos, images, scenarios, and capturing their emotional responses, including speech. For example, um, there's a very emotional movie, or you know that if you watch that movie, it is going to trigger sadness in your it will kind of make you upset. So somehow, when after showing that video, you can ask the person a few questions. Now that when they will respond, then it might be possible that you will be able to capture the sad voice, right? You have shown them something to make them sad, and then you are recording their speech data to capture the sad voice, right? This is the elicited emotion data, similar to what we did in the facial expressions category, because we showed them a picture or a video, and you felt something like disgusted. Suppose disgusted, I feel disgusted, so my eyebrows will be like this. So similarly for the speech as well. So which category of voice-based data includes induced emotions in participants through stimuli, such as videos and then capturing their speech responses? This is elicited emotion data. Okay. Okay. Which dataset consists of recordings of 10 German sentences spoken in different emotions by actors? This is a very factual question. So, if you want to try, and if you have attended the lectures, I think you must have heard about these datasets at least. Berlin database. Okay. Okay. So yeah, this IBO database, it's audiovisual recording of humanoid robo called IBO. Okay. This Berlin database for emotional speech, it's a emotional speech dataset containing recordings of German sentences. by professional actors in 7 different emotional categories. This database matches the description provided. Okay, yes, this is the correct answer. Uh, and this Ryerson audiovisual database, this is the specialty is that it also contains the music element, audiovisual recordings of emotional expressions by singers and actors. So this also has music data. Okay, so the correct answer is Berlin database of emotional speech.
Yeah, ma'am. Is there any such database which is natural, like I mean, actual? It's not based on actor database or actors' spoken languages.
Uh,
Is there any such database available?
oh, sorry, ma'am, I did not catch you. Are you asking about a natural data set?
Yeah. I mean, naturally recorded
Yes,
environment, right?
I'll have to look for it because I'm not aware. Right now I can't recall. But I
Because all such data sets that are openly available or anything like that, these are either busy or, I mean, actor data sets.
yeah, mostly acted because it's relatively easier to, you can say, label, and more
Yes, yes,
more
exactly.
more it's like more the privacy concerns are also there. Also,
Hmm.
another thing is that labeling is also very tedious sometimes because matching.
Labeling will be tedious because I mean, like opposite emotions, joy and sad. These things you can get correctly, but other
Yes,
emotions it is difficult to catch.
yes, yes,
Okay,
yes,
ma'am.
yes, yes. So I'll look for it in the next session. Maybe I can share if I find some open source natural data set. So I'll definitely share. Thanks for the question. Okay. Um, yes. Which of the following are major challenges in voice-based affect analysis? Limited availability of emotional speech synthesis, lesser accuracy than FER systems, um, scalability of datasets, cross dataset performance across different languages. Oh, I think there is a typo here. I think there is a typo. We want to know not a major challenge, which is not. Sorry for the typo. Not a major challenge. If you would like to update your answers. Okay. So actually,
Is it one
okay,
limited availability of emotional speech synthesis?
let's see. Um, this is, I think, many challenges are there, but we need to select what is the least of our concerns because I can see all of them are kind of uh, big challenges, right? So we would select the least bothering one, right? Um, First is limited availability of emotional speech synthesis. Of course, this is a major challenge because we don't have many data sets, right? Second is lesser accuracy than FER systems. Do you think this is correct? Because I don't think so.
Yes, this is not lesser accuracy. How do you know? This is not a major challenge, I think.
We can't generalize, right? And we
Hmm.
can, of course, always design a better model than
Hmm.
we just can't compare. Scalability of data sets, of course, it's a major problem. If we have, for example, 10 speakers currently and we want to expand the data set, now we want to include 10 more speakers, we need to take care about a lot of things. Um, Firstly, to gather such people in a setup, it's very time consuming, very resource intensive also. Number two is the privacy concerns. We need to get the form signed, then consent forms, declarations, uh, sought permission from, seek permission from higher authorities and all. So in previous lectures, we also discussed about there's a committee for the ethical consideration while we are performing some kind of analysis or survey or data collection. So yeah, so that is also, I mean, one of the important factors that we need to consider, and it is actually very tiring and very time consuming, very resource intensive. So scalability is a major problem, right? And another major problem is cross dataset performance across different languages. Even if we have one system designed for English, might not might not work well for Hindi or any other language, right? Because every language has their own characteristics. For example, in some languages, some sounds are exclusive to them only. So the model is unaware of what is happening in that new language. So most likely the model will fail. They usually don't produce good accuracies cross data set, even if it is on the same same language. Across languages is the whole different concept. Like it's a whole different difficulty level. But I would say, even if it is English based data sets and two different data sets you take to train on one data set, and then you kind of evaluate on another data set, that is also going to show you a lot of degradation in the performance, because this is a major problem. We don't have the generalizable robust models yet. So that is an open problem. And of course it's a cat and mouse. Like something will uh, this is in case of emotion generation, or like other problems like deepfakes or any other. So one thing improves, then the other thing it offers some disadvantages, and then another algorithm approves to counter that, and this chain goes on and on, right? So this will this will become outdated after some time, and we need more sophisticated. This is never ending process. So yes, we need more sophisticated models as well. So this is not a major, the least bothering, you can say. Okay. Which features are commonly used for automatic feature extraction and speech analysis? Is it syntax and semantic features, prosody and spectral characteristics, phonetics and phonology features, pragmatics and discourse features?
B
Sorry, which one?
is B. B.
B.
Prosody features and spectral characteristics.
Okay, okay. Yeah, yes. Let's go through all of the options one by one. So the first is syntax and semantics features. Syntax, mostly they are more grammatical in nature, right? More on the linguistic side. So they're not typically used for automatic feature extraction and speech analysis, unless your application is like more of a um, you can say something related to the language, the correctness of the language. But here we're more concerned about the feature extraction from the speech data, not exactly like, am I saying, is my grammar correct or not? So this is something that we don't usually consider, okay? So they feature relate to the grammatical structure of sentences and the meaning of the words, not typically used for automatic feature extraction. Second is prosody features and spectral characteristics. Yes, this is correct because as we already discussed that prosody means the way you say something, like the tone, the pauses, the your basically your style of saying something. I we all follow different prosodies. So the stress, the rhythm. So these things come under prosody. And also spectral characteristics. Spectral information is more like the frequency domain information, right? And time domain, frequency domain information that we are actually the handcrafted features. You can say that fundamental frequency, pitch, loudness, these kind of things also. MFCCs, you must have heard about them, Mel frequencies, Sepstrom coefficients. So one of the very famous features. So yeah, this is correct. Phonetics and phonology, they are more related to the sounds of the speech and study of how sounds function within a particular language. We're not that concerned with how the sounds are present within a language. We're more concerned about more real life, like not we are more concerned towards more directed applications, right? So not typically used for automatic feature extraction. Pragmatics and discourse. Pragmatics is the involvement of context. So language of context, like sarcasm, or it requires a lot of other information, contextual information. You can't like you can say something. Oh, why don't you quit your job and start following your passion? If your boss says this to you, there might be different contexts, like he might be sarcastic or he might actually mean it, looking at your, you can say, interests. So it depends a lot on the contextual information. Okay, this is something that we don't consider yet because we're not that, we just want to achieve a basic analysis still, sophisticated algorithms for the time being. However, in future we can definitely, um, I think, progress towards these kind of information as well, because for example, say a few, not a few, I mean many years from now, if robots become the normal, the new norm, and they are also living with us in our houses, and they sense, okay, what is the environment going on, by listening to our conversations they can get the context, and then they can respond accordingly. They can also sense sarcasm. Sarcasm is something that humans can sense, right? Not the machines yet. We're not that capable yet. But of course, in future we may see some works on this as well, but for the time being they're not commonly used for feature extraction and speech analysis. Okay, so yeah, this is prosody and spectral characteristics. Which library can be used to extract MFCCs from audio signals? If you have used Python for any yeah, Librosa. Librosa.
Prosa?
Okay, okay, yes. So I think everybody is aware about this. So, but still, I would like to discuss. So TensorFlow is mostly a like framework. It has been developed by Google. It provides tool for building and training various type of ML models, DL models, right? And TensorFlow is used for tasks, different tasks, NLP across different modalities as well, right? It is more generic, more focused on the machine learning and deep learning aspects rather than focusing on a specific modality. Okay. Diva ma'am, can you please mute?
Yeah, yeah. Sorry,
Oh,
sorry, madam.
it's okay, it's okay, it's okay. So, okay. Um, okay, next is scikit-learn. Scikit-learn is a Python library. It is also for the ML learning, but it is more designed to handle more complex functions or helping functions, you can say. Okay, it is mostly for the data mining and data analysis. Now, this is a library actually, and this is a framework. TensorFlow is a framework. Now, scikit-learn, it includes different algorithms for classification. For example, k means or k nearest neighbor. You can just import and use. Okay, Librosa is something very specific to audios. Specific to audios. Um, Audio and music analysis. If you have used Librosa, uh, you can just extract any kind of features like librosa dot extract mfcc. I don't remember it exactly, but this is how with a simple like line you can extract mfcc from the input signal, or you can display input output, extract some amplitude value, power spectrogram. So yeah, zero crossing rate, again, so many features are there, many features are there. So you can use Librosa for your analysis. If you're starting to work on audio analysis, then definitely you should check that. And the best way, this is kind of um, out of the scope, not scope actually, but I would like to say the best way is to go through the documentation, and you will see what you can do with that library. So you should explore what kind of features you can extract directly using Librosa. So yeah, um, this can be used for extraction, feature extraction, visualization, and manipulation of audio data. And the applications are speech recognition, MIR, music information retrieval, genre classification, audio classification. So numerous applications. NumPy is a more fundamental library package. Okay, it is for scientific computing. We usually deal with arrays. You want to convert to list, array, mathematical functions, matrices. So these kind of things are mostly, and also this is not specific to audio analysis. So this is a generic one. So yeah, this is Librosa. Okay. Which feature is commonly used to measure the energy in an input acoustic signal? Is it loudness, fundamental frequency, formant frequencies, and speech rate? Energy in an input signal.
Hormone frequencies.
Formant frequencies, okay. Anybody else would like to answer? So, okay. Firstly, loudness. Loudness, it refers to the perceived intensity or the volume of the sound, right? I'm talking slowly right now, and I'm talking very loudly right now. So there is more energy in my, how am I sounding? It's a measure of the energy present in an acoustic signal. Okay, and loudness is measured in decibels. It can provide valuable information about speaker's emotional state as well, because or the emphasis placed. If you are angry, um, you might shout loud, right? So it's more loud. So you can observe that generally what the high arousal emotions can be more more high energy. right? In your voice as well. So this can be one observation for angry emotion. Okay. Um, Second is fundamental frequency. We've discussed this now quite a few times. So again, it is the lowest frequency of the vibration of the vocal cords during speech. It is um, related to the pitch of the voice, perceived musical pitch of a note. It does not directly measure the energy, right? It's more frequency side. Then formant frequencies, they're resonant frequencies. As I mentioned, like the vocal tract, how it is built, how it is being modulated. So you modulate the clean, kind of clean, plain signal, and you modulate it, and then it converts into something complex. So this is where the formant frequencies come into picture. And they also they are related to the shape and configuration of the vocal tract and quality of speech sound. They can be used as a feature. However, they don't directly measure the energy in the acoustic signal. Now, speech rate is refers to the speed at which speech is produced. Words per minute, syllables per second. Some people talk like really slowly, and some people are like very fast. You can't understand what they're saying. So the differ in the speech rate. Okay, while speech rate is an again important feature, it also doesn't directly measure the energy. So
It's the loudness.
yeah, it's the loudness. Yes, decibels. Okay. Um, which attribute is commonly associated with positive voices in speech analysis? Low loudness, consistent pitch, high loudness and variable pitch, low pitch and variable loudness, high pitch and consistent loudness. Karishma ma'am is saying B.
It's D. D for drum.
High pitch and consistent loudness.
Yeah.
Okay, let's see. So, positive voices in speech, they're mostly commonly associated with high loudness and variable pitch. Uh, like we discussed briefly, that if you are feeling sad, it's more likely that you will talk on a very you know consistent pace without too much variations in your speech. Like I will read the sentence in both manner. Positive voices in speech analysis are commonly associated with high loudness and variable pitch. So this is more of a sad version. And what is a happy version or a positive? Positive voices in speech analysis are commonly associated with high loudness and variable pitch. So you can sense that there is more variation out there, right? And more positive emotions such as excitement, enthusiasm, or joy, we usually talk with increased volume or high loudness, and we exhibit fluctuations in pitch, reflecting the its more dynamic and expressive nature, right? We're more excited, we're more happy, and we like to express in a more dynamic way rather than more bland way. So, second option is correct, high loudness and variable pitch, because I will modulate my voice quite often, right? Okay, why is speaker normalization applied in speech-based emotion recognition to standardize the emotional content of speech across different speakers, to enhance the differences between angry and neutral speech, to accommodate variations in speech features introduced by differences in speakers' vocal qualities, to eliminate the differences in emotion expression caused by speaker variability. We should just take a minute to read this question out and then try to answer. C. Okay. D. Okay. Let's discuss what happens is that speaker normalization, we aim to standardize the features extracted from speech across different speakers. Okay, um, why do we want to do that? We want to do because we want to ensure that the analysis is not biased by individual differences in vocal characteristics. Example, we have 10 people in our data set, 10 speakers. Now every speaker will have certain different characteristics. And suppose our objective is to determine the emotion present in uh, you know speech signal, right? We want to detect the emotion. Now it is quite possible. Uh, Suppose I am using pitch as a feature or fundamental frequency, right? I'm using fundamental frequency as a feature. Now, this feature, um, it is possible that my neutral voice is higher in pitch than a male's excited voice. This is because there's difference between my voice and his voice, right? Because as we have discussed, like males and females, they have different distributions, kind of for the uh, many features. So we want to just eliminate that thing and focus on the emotional part only, so that we only focus on the relevant part, and other factors influencing our decisions, they are eliminated as much as possible, right? So normalizing, what it helps is it brings the features values into certain range. Males will also have the value between 0 to 1, and female will also have 0 to 1. So we can kind of normalize using different strategies, and then we can eliminate that unnecessary bias, right? So we can focus more on accurately emotional content of the speech rather than being influenced by inherent variability in speakers' voices. We improve the generalization and robustness of the emotion recognition systems across diverse speaker populations, right? Example we will see. Let's say I have two speakers. Okay, two speakers, one with naturally high pitched voice and another with a naturally low pitched voice. If we don't normalize their speech features, this system may mistakenly associate high pitch with one emotion and low with another, and it will lead to misclassification. But if I apply speaker normalization, we can adjust for these individual differences and focus solely on the emotional cues present in the speech, irrespective of how the speaker is, his voice is, their voice is. So, speaker normalization, it ensures that the emotion recognition system remains robust and reliable across diverse speakers. Now, if there's another third speaker is coming into the picture, and the system is able to handle that variability and tell, okay, this emotion is being expressed. So, C is the correct answer. First is to standardize the emotional content. We don't want to standardize the emotional content. I mean, it's not true, it's not false either, but not the best description, right? To enhance the differences between angry, no, this is not relevant. C is correct. To eliminate differences in emotion expression, no, we don't want to eliminate the difference, right? We want to enhance it. We want to eliminate the variability part, right? So, next question is what technique is commonly used for speech based emotion recognition? A very famous method. Okay, okay. So, so the thing is that these methods, this is an ML algorithm, like ML. This is also ML. This is suppose deep learning. They're not features. We're talking about like features here. This is a technique. Um, Actually, the question is wrongly framed. I would like to say that we can use all of them like as a method, but as a feature, this spectrograms is what the question intended to. But okay, let's move on with. So spectrograms. What do we mean by spectrograms? Spectrogram is a pictorial representation. Pictorial representation of an audio. It contains frequency and time information plus the intensity also. So three kind of information we are preserving here. Okay, so it becomes really insightful to use spectrogram as a feature. What it has is frequency on the vertical axis. We have like this is hertz. Okay, let me use another color. This is hertz. Then the time on the horizontal axis, seconds. Suppose you have 10 seconds audio, so this will be 10. Okay, and intensity is also there. Like at every position, there will be some dark or light, like this kind of thing will be there. So this is something, this is what the spectrogram looks like. I'll show you a picture also. So spectrogram frequency is represented on the vertical. Lower frequencies are typically at the bottom while higher on the top. Time on the horizontal axis. Okay, left to right. Intensity is the amplitude of each frequency component. Darkness or the color intensity. Whatever color scheme are you using, um, it will stronger or louder frequencies. Like what is the intensity of that frequency? If it is more intense, then the color will be darker. If it is lighter, then it means that okay, intensity is low. Okay. Frequency resolution. How do we, you know, define the frequency resolution? It depends. A higher frequency resolution, higher frequency resolution allows uh, for a better distinction between individual frequency components. The more, I mean, the more quantization and that we have, better distinction between individual frequency components, while lower resolution provides a more generalized way. Of course, if it is more detailed, higher resolution means more detailed, we can peek into that little frequency bins as well, like between even within the range of suppose 10 hertz, we can figure it out. Okay, this particular frequencies are also. If it is low resolution, we can just get an overview. Okay, this audio contains mostly high frequency, we don't want to go into the details. So frequency resolution is there, time resolution is there, that we can use time window analysis. For example, usually what is done is we have an audio, usually 10 seconds, suppose, right? A few seconds, 2 seconds, 10 seconds, 5 seconds, whatever. So say 10 second, and it is like huge to be processed. We need to divide into chunks. And this chunks, basically what happens is that when we divide an audio into chunks, we don't use like chunks, we use a window, sliding window. Okay, and that window can be overlapping. For example, we want to calculate the frequencies present, and the window size might be 25 milliseconds or so, very small window. And within that range, within that time frame, we will calculate all the frequencies present, and then we can display, like, okay, we can get a spectrogram corresponding, and then we can kind of stitch the spectrogram together to obtain the overall spectrogram. So this is how it works. So yeah, time resolution is there. Temporal shorter time windows provide better temporal detail, but frequency resolution will be might be sacrificed, while longer time windows offer better frequency resolution but may lose, because time and frequency are kind of opposite, right? Not kind of, they are opposite. So this is how a spectrogram looks like. If you zoom into, you will see there are, this is actually discrete, right? If I may zoom into this, you can see um, the darker, okay, let me use this. Here you can see the intensities. If we talk about the purple color, if we consider the purple is more, then this is high intensity, this is low intensity, and this corresponds to, this is the time, this is the frequency range. Okay, and this can be used for different emotions. Um, you can observe that, okay, usually angry emotion audios, they exhibit this pattern, they show this pattern. So you can observe that pattern using some deep learning algorithm or machine learning algorithm, and then you can figure out patterns from the data, right? This is how you can use the spectrograms. And for different emotions, you can see, for example, angry, uh, you might observe, okay, something like high intensity going on here, right? And then fearful is, you see there is a pattern, fearful, like there are, if you observe it closely, this is a kind of recurring pattern, right? Here also, um, if it is sad, it's more purple. Okay, but if it is calm, then it's more yellow. So these kind of patterns you can observe, and yellow and purple means high and low intensity. Okay, so yeah, this can prove as, and this has proved as a very good feature. So next question is, okay, we need to answer this. So the answer is spectrograms. The answer is spectrograms. Okay, next, and the last question for this session. Um, what is a major concern regarding the real-time applicability of speech-based affect recognition systems? Lack of robust algorithms for feature extraction, variability in emotional expression across different individuals, computational complexity and potential exhaustion of resources, limited availability of labeled emotional speech datasets. Again, this is, you need to decide the best one, like C, D. Rishabh is saying D, limited availability. Hmm. I would say please read the question again, because you might find something useful keyword to answer the question. Rishabh says A, Niva ma'am B, Karishma ma'am B, C. Okay, okay, we have three three different options. Okay. Since we're talking about real time, and real time is usually it mostly, I would say, mostly it's expected for models to perform well in real time scenarios. We need speed, and for speed we need lesser computation, right? If the model is very complex to be deployed on a small device like mobile phone, yes, then we need smaller, light, lesser parameters to be deployed on um, low compute devices, right? So lack of robust algorithms, we can develop robust algorithm. It has, okay, it is a concern, but it's not related to the real time applicability, right? And variability in emotional expressions, this is also something we need to work, like, for the improvement of accuracy of models, not real time. This is this is important, computational complexity, because we have limited resources. Real time means limited resources, sometimes limited resources on say smaller machines. Another factor is the speed we need, right? And if complexity is high, which means um, more number of parameters, right? More parameters, more computation required. So we need to focus on how to make the models less complex and less resource intensive. So uh, this is about the this is about this real time applicability. Okay, and with this we reach the end of this session. I hope it was helpful in some way, and I tried to include uh, last presentation. Oh, I will check. I think I uploaded that. I will check it out. Maybe I will upload both by today, so you can check them out. Might be possible मैं भूल गई होंगी, so I'll do it. And okay, so we have live sessions every Tuesday 6 to 8, and next session will be 5th of March. And if you have any queries, any doubts, uh, you can also ask in the next session. So I hope this session was helpful, and it would be great to see you in the next sessions as well.
Yeah, thank you very much, ma'am.
You're welcome. You're welcome. Thank you for joining. And
Sorry, ma'am, I got late.
uh, there was one book mentioned in the description of this course. You can check it on the home page where the course description is there. I don't remember the exact name, but there are resources mentioned. Okay, let me check. Let me check right now. Course. I think. Okay, please wait for 1 minute. Um, Affective computing. Okay, about the course. This is I'm just copying paste. I'll just copy and paste in the chat box for your reference. Yes, yes, yes. Uh, yes. I think you should the first two, I would say, because third and fourth are more HCI centered, right? And the first book is more like completely focused on the effective computing. I think you should try the first reference. Although I'll be very honest, I have not gone through like the complete book, these books, because usually we use web and different resources. But I think I've heard about this book, so you can check it out. Okay. Any other doubts? Thanks, Rishabh. Thanks. Okay, so we can leave the meeting.